So today I'm going to be talking about eigenvalues and what effects they may have on a matrix. So let's say that I have a matrix A, and it's going to be a 3 by 3 matrix, so it's going to be a square matrix. The first row is going to be 1, 2, 3. The second row is 0, 4, 5. And the third row is 0, 0, 6. And we want to find the eigenvalues of A. So then the eigenvalues of A have to be figured out by this determinant formula. The determinant of A minus lambda I is equal to 0. Now when we find the determinant, we're going to have to use a specific process for each matrix, and a matrix A subtracted by the identity matrix times lambda is going to give the effect of subtracting lambda on the main diagonal of the matrix. So if I do that, what's going to happen is every element that's on the main diagonal is going to be subtracted lambda. So we're going to have 1 minus lambda, 2, 3. These two elements are not on the main diagonal, so they're not going to be subtracted. 4 minus lambda, 5. And then on the bottom row I have 0, 0, and 6 minus lambda. So now that we've subtracted lambda on the main diagonal, what we want to do now is we want to find the determinant of this matrix. So starting off with the first row and the first element, I have 1 minus lambda. So we're going to begin with that in mind when we do this. So starting off with 1 minus lambda, what we can do is we can consider only this matrix down here, this 2 by 2. So crossing out this first row and this first column, we're only left with this matrix to find the determinant of. So when we do that, we have 4 minus lambda times 6 minus lambda, and then I have to subtract 5 times 0, which would just be 0. So now that we're done with that determinant, we need to subtract the next element that's on the first row, this 2, and then we're going to create the cofactor matrix, kind of similar to what we did last time, except we are going to only put dotted lines on the first row and the second column. So like this. So the first row and the second column get the dotted lines now. So now I'm just left with the 2 by 2 matrix consisting of 0, 5, 0, and 6 minus lambda. And if I take the determinant of that matrix, I'm going to end up with 0 minus 0. So that would just be 0. So next I'm going to circle the last element of the first row. I'm going to give it a positive this time instead of a negative. And then we're going to find the cofactor matrix. And the way we'll do that is we will put a dotted line through the first row and the third column this time. So now what we're left with is this 2 by 2 matrix right here. The 0, the 4 minus lambda, and then the 0 and the 0. But when I take the determinant of that matrix, I get 0 minus 0 again. So now these two terms are going to become 0, and I'm only left with this right here. This is my characteristic polynomial. 1 minus lambda, 4 minus lambda, and 6 minus lambda. So now I'm going to set it equal to 0 and find the roots of the characteristic polynomial. And the characteristic polynomial is composed of factors that I can individually set equal to 0. So if I set this factor equal to 0, I'm going to end up with lambda equals 1. For this one, I'm going to end up with lambda equals 4. And for this one, I'm going to be left with lambda equals 6. So these are my 3 eigenvalues. Now notice, because this top matrix that we used is an upper triangular matrix, we could have used the main diagonal to find the eigenvalues. So what that means is, if you have an upper triangular matrix where everything below the main diagonal is zeros right here, what you can do is you can use the main diagonal of the matrix to find the eigenvalues that you need. So here's where 1 comes from, right here, and here's your 4 that we found, right? And here's your 6. So that demonstrates the fact that the eigenvalues of a triangular matrix are simply the entries on the main diagonal. So finding the eigenvalues is easy in this case.